Hello, I'm Dr. Colleen Jones, the lead principal investigator for our collaborative project titled Verification of Atmospheric Mercury Redox Rates. Our goal is to understand how elemental mercury changes into more toxic oxidized forms using simulated atmospheric conditions. To do that, we're making high-quality measurements of elemental mercury, oxidized mercury, and the oxidants that drive these reactions. We use models to evaluate proposed oxidation mechanisms and will update them with reaction rates validated through our experiments. This project also expands on our capabilities with a large 35 cubic meter environmental chamber system, an upgraded dual channel instrumentation, and hands-on training for students across USU, BYU, UNR, and the University of Utah. You'll now hear from several members of our team who are making this work possible. Dr. Hansen's environmental chamber systems gives us control conditions to measure mercury chemistry accurately. Our entire team across all 4 universities work together to design and build the environmental chamber system.
Hello, my name is Jaron Hansen. I'm a professor of chemistry here in the Department of Chemistry at Brigham Young University. And I'm one of the collaborators in this wonderful project that is designed to measure how mercury, elemental mercury, when it gets emitted into the atmosphere, gets converted into its more toxic form of mercury 2+. And in my lab, we have a large environmental chamber that we can fill up with controlled trace amounts of mercury, and then we can introduce other reactants into that bag, and then we can monitor the progress of mercury as it gets converted into mercury 2+. We use a variety of instruments to do that, from broadband cavity enhanced absorption spectroscopy to other commercially available techniques to measure oxidant concentrations. And we're looking forward to the results of this project, and hopefully it will do some good in the world in helping to understand how mercury gets transformed into its more toxic form.
At Utah State University, Dr. Seth Lyman's work helps us to understand why real-world mercury chemistry does not match what the models have predicted. His over a decade of experience designing instruments that accurately measure oxidized mercury species are central to this project.
Hi, I'm Seth Lyman. I work at Utah State University at the Bingham Research Center. I'm the co-PI on this project for USU with Colleen Jones. I'm really excited about this project because some previous work that we've done with measurements and modeling has shown that what we think is happening with mercury chemistry in the atmosphere is not what's happening. There's more or kind of faster chemistry that's turning elemental mercury to oxidized mercury. So we're hoping with this project we can figure that out better so that we and regulators and governments can understand when mercury gets into the air, where's it going and where does it end up as it travels through the atmosphere and deposits into ecosystems.
Turning scientific ideas into real working systems requires strong technical leadership, and that's where Trevor O'Neill shines.
Hi, I'm Trevor. I'm a research scientist here at Utah State University, and I was asked, what have I contributed to this collaborative research project for oxidized mercury that we've been working on? And in a nutshell, my job is to take these great ideas that these scientists have come up with and to make it real, to facilitate the infrastructure, the processing of the data, communications, and materials procurement to be able to make it real. With that, at the same time, to educate undergraduate and graduate students how to mitigate those hurdles that we run into when we are doing science that hasn't been done this way before.
Our undergraduate researchers at USU keep this project moving every single day. Carly and Tristan play essential roles in instrumentation, calibration, and data quality.
Hi, my name's Carly Zager. I'm an undergraduate research technician, and my job on this project is maintaining and troubleshooting our mercury quantification instrument called the dual channel. I think the most important thing that this project has taught me is that you learn way more when things go wrong than when they go right, and that the best experience you can have is troubleshooting systems, and it gives you real-life problem-solving skills, and nobody else in the world knows how to work this instrument like I do, and I think that's pretty neat.
I'm Tristan Coxon. I'm an undergraduate researcher at the Bingham Research Center. On this joint study between BYU and USU, I was in charge of putting together Calibrator 4. Calibrator 4 is a mercury dilution calibrator, which are just fancy words, which means it pulls helium through and actually dilutes mercury to a point we can measure inside the dual channel to make sure it's measuring mercury correctly. I learned a lot about putting together electronics and different parts and making them combine together in a system that all works together.
At BYU, our student collaborators are building instruments, running chamber experiments, and pushing forward the next generation of atmospheric mercury research.
My name is Alexis. I have helped on this project by building the bag and having my instruments in the bag, which are the spectrometers looking at the different chemical species. I also run all the instruments during experiments, and I've been learning more about kinetic rates of what's going on in the atmospheric reactions, and that will help in my future as I'm continuing to do other reactions or more mercury reactions, just studying those kinetic rates.
Hey, I'm Callum Flowerday. I'm a grad student here at Brigham Young University. I helped create the instruments, specifically the cavity instruments for measuring BRO and bromine and hydroxyl radical. I also helped set up the bag, and it's been good. This will help me get some experience for chamber studies in the future, and gives me an application for the instruments that I've built. My name is Zach Duke, and some of the main things that I've helped with on this project are for our HONO and bromine instrument, I made something that will automatically raise up the purges so that we can calculate a mirror curve. During experiments, we don't have to go in and out of the bag. I'm also helping monitoring the VOC levels. I made this little sampling box, and we draw air in through a thermal desorption tube, and it'll calculate the live flow, and it'll do it for whatever time and whatever volume of gas you want to sample. Some other things, just I helped make the bag, general maintenance things, drilling holes in the Teflon plate, things like that. And I've learned I learned some more technical skills. I've been doing almost more like the engineering things, like programming Arduinos and 3D printing stuff. And I'm going into medicine, so I'm sure that those analytical skills will help me there. And it'll help me to maybe understand instrumentation that I use as a doctor one day a little bit better.
We also have several key collaborators whose work is essential to this project. At the University of Nevada, Reno, Dr. Sarah Dunham-Cheatham and Dr. Mae Gustin lead our oxidized mercury speciation work using thermal desorption membrane methods. Their measurements help us to identify which form of oxidized mercury is being produced in the environmental chamber. At the University of Utah, Dr. Jessica Haskin and her student Jackson Coley are leading the modeling component. Their work links our chamber results to real atmospheric conditions and global mercury transport using models of oxidation mechanisms updated with reaction rates validated by our experiments. At Snow College, Dr. Ryan Thauman supports this project through instrumentation design, fabrication, and system optimization. Together, this multi-institutional team is generating some of the most precise and comprehensive measurements of mercury redox chemistry to date. We're grateful for the National Science Foundation's support and for the contribution of every collaborator and student who makes this work possible.